Hello, this is the third video in the amount of substance topic. Today we're going to be looking at how you can calculate empirical formulae, reacting mass calculations and limiting reagents. So the checklist, so by the end of the session you should hopefully be able to calculate empirical formula, calculate the value of X in hydrated salts, and calculate masses from balanced equations, including identifying the limiting reagent. So the first thing I thought we'd look at is empirical formulae. Empirical formula is the simplest whole number ratio of atoms in a compound. So this would be something like CH2. The molecular formula is the actual number of atoms in a compound. So for example, C2H4, that would be the molecular formula. That tells you how many atoms there are in the compound. You can simplify that down to come up with the ratio, which is CH2, which is the simplest whole number ratio. Okay, so a quick recap. To calculate moles, we need to do mass divided by relative formula mass. We looked at this in the previous video. So, the general steps how you calculate empirical formula. First, you need to identify the elements that they're talking about. Use the mass. This can either be the mass in grams or you could use a percentage. You can then write the atomic mass, work out the moles by doing mass divided by relative formula mass, and then you work out the ratio, which you get by dividing by the smallest number of moles. Let's have a look at an example. So compound X has an MR of 62. It contains carbon, hydrogen and oxygen. It has 38.7% carbon, 9.68% hydrogen by mass. Calculate the empirical formula of X. So the first thing we need to do is we need to find the relative atomic masses of carbon, hydrogen and oxygen, and we use our periodic table. So carbon is there, it's got a relative atomic mass of 12, hydrogen has got a relative atomic mass of 1, and oxygen has a relative atomic mass of 16. So I'm going to fill out this table. Okay, so the mass of carbon is 38.7%, 38.7. The mass of hydrogen is 9.68. Remember, we can use the mass in grams or percentages. The mass of oxygen, well, the compound only contains carbon, hydrogen and oxygen. If 38.7% is carbon and 9.68% is hydrogen, then it follows that 100 minus 38.7 minus 9.68 is going to give you the mass of oxygen, which is 51.62. The atomic masses, we just got those from the periodic table. So the atomic mass of carbon is 12, hydrogen is 1, oxygen is 16. Calculate the moles. To do that, we just divide mass over MR. So we're just going to divide 38.7 by 12, which will give us 3.225 moles. Hydrogen, we do 9.68 divided by 1, which gives us 9.68 still. And oxygen, we do 51.62 divided by 16, which gives us 3.226. Don't round these numbers up too much, leave them quite full in the calculator, and that way you get a more precise answer. Okay, so now for the ratio, the hardest bit. We look at these three numbers here and we choose which one is the smallest. Well, 3.225 is the smallest, but it's basically the same as 3.226. So we're going to divide all of these numbers by 225 rather. So the moles, 3.225 divided by 3.225 is 1. 9.68 divided by 3.225 is 3. These should be integers, by the way. And 3.226 divided by 3.225 is 1. So the ratio is 1 to 3 to 1, which means we've got 1 carbon, 3 hydrogens and 1 oxygen. So it is CH3O. Okay, so also we were told that the MR of the compound was 62. We've calculated that it's CH3O, so now we need to know the molecular formula. Okay, so the way we can do this is we know the atomic mass of carbon is 12. We know that there are 3 hydrogens and each one is 1. and we know oxygen is 16. So we know that 12 times something plus 3 times something plus 16 times something must add up to be 62. So what is that something? So let's gather all of these terms together. So 12 plus 3 plus 16 is 31. So 31x equals 62. So therefore x equals 2. So we just need to times everything in this formula by 2, which gives us C2H6O2. Final check. 12 times 2 is 24, plus 6 is 30, plus 2 times 16 is 32, added that to the 30 is 62, so this is our molecular formula. Okay, so we're going to have a think about now the water of crystallization questions. These are the ones that involve the XH2O. So for example, you might have copper sulfate dot XH2O. Calculate how many moles of water are produced. So this is the experiment where you're going to weigh a hydrated copper sulfate, for example, or a hydrated salt, and then you're going to heat the hydrated salt until all the water has been removed from the salt. Now the way you'll know that all the water has been removed from the salt is you're going to heat, and then you're going to weigh, and then you're going to put the crucible or the evaporating basin back onto the Bunsen burner, heat again, and then reweigh, and you're going to keep reweighing and heating until the mass stays the same. Once the mass stays the same, you know that you've removed all of the water. So it's this expression, heat until constant mass. It's really common. It's a really common exam question, and if you're asked to give the method, it's really important that you say heat till constant mass. Okay, so the method is, and the reason I've lumped this in with the empirical formula is because this is essentially an empirical formula calculation. So this time we need to use the mass of anhydrous salt and water, the MR of the anhydrous salt and water. You work out the moles by doing the mass divided by the MR and the ratio. Now I've put water in bold here, and it also needs to be the anhydrous salt, so the salt without the water. That's really important. So let's have a look at an example. A student heated 4.38 grams of hydrated zinc sulfate and obtained 2.46 grams of anhydrous zinc sulfate. Use these data to calculate the value of the integer x in ZnSO4.XH2O. So it's ZnSO4, that is the anhydrous salt, and water, that is obviously water. So it's the MR of this that we need to find out, and the MR of water. So we need to use our periodic table, find zinc, sulfur. So we need to calculate the relative formula mass of zinc sulfate, which is ZnSO4. So the relative atomic mass of zinc is 65.4, oxygen is 16, sulfur is 32.1, and we also need to work out the relative formula mass of water, where oxygen and hydrogen, the relative atomic mass of hydrogen is 1 and oxygen is 16. Okay, so we'll go back to the question. A student heated 4.38 grams of hydrated zinc sulfate and obtained 2.46 grams of anhydrous zinc sulfate. So we're going to make our table. So we're going to have zinc sulfate here, and we're going to have water here, and then we need the mass, the MR, and the moles. So I always remember this is mass is Mr. Moles, and then we need the ratio. Okay, so the mass of zinc sulfate is going to be 2.46 grams. It's important that we use the anhydrous mass of zinc sulfate. The mass of water we need to calculate. So 4.38 grams is this substance. The 2.46 grams is this substance. So the mass of water in there is 4.38 grams minus 2.46 grams, which equals 1.92 grams. So that is 1.92 grams of water. So the relative formula mass, so we just looked up the relative atomic masses. So zinc is 161.5 and water is 18. Moles, to work out moles we do mass over relative formula mass. So it's 2.4 6 grams divided by 161.5, which is 0.01523 ... We're not going to round just yet, and the water is 0.1066 recurring ... Okay, so just did 1.92 divided by 18. The ratio, just like an empirical formula, we divide by the smallest. Well, the zinc sulfate is the smallest number of moles, which is 0.1523, which equals 1. And then we divide this by 0.01523, which equals 7. So the answer is 7. It needs to be an integer, so that means a whole number. So x equals 7. Okay? Reacting mass calculations. So I'm only really going to look at this briefly because there's not actually very many exam questions that come up that just directly ask you for a reacting mass style calculation. Okay, so to work out the reacting mass, we essentially need to use the balance symbol equation to calculate the mass of a product made or the mass of a reactant needed in a chemical reaction. Most of the questions will usually involve using concentrations or using PV equals nRT or some other form of equation as well. You're unlikely to just be given the mass of one reactant and asked to calculate the mass of the product. But how you do this is you take the mass of the known and you work out the MR, you work out the moles of the known. So by known I mean this is the one you know the mass of this, so the mass is known. Then you work out the ratio of moles from the chemical equation, and then you can work out the mass of the known. Okay, we're going to be using this equation all the time. So to work out the moles, we use M over MR, and to work out the mass of the unknown, we're going to use MR times N, which equals mass. So that's just a rearrangement of this equation. Always best done, I think, with an example. Calculate the mass of sulfur trioxide formed from 32 grams of sulfur dioxide. So the question is asking us to calculate the mass of sulfur trioxide, so that's this, and they've told us that 32 grams of sulfur dioxide, so we know the mass of this. So it's important with these mole calculations that we start with the thing that we know the most about, which in this case is sulfur dioxide. As always, we're going to need the periodic table to work out the relative atomic masses. So we can use the relative atomic mass of sulfur, which is 32.1, and oxygen, which is 16. So back to the question. Again, I've made a little table here. So the mass of sulfur dioxide is 32.0 grams. We've not been given any information on oxygen, so I'm just going to ignore that. And sulfur trioxide is what we've been asked to calculate, so that's our X essentially. So the MR of sulfur dioxide, so it's 32.1 plus 16 times 2. A common mistake when working out relative formula mass here is to include the stoichiometry, so the big 2 in front of the SO2. Don't use that here because we are going to use this when we get to the ratio step here. So the relative formula mass of sulfur dioxide is 32.1 plus 32, which is 64.1. The MR of sulfur trioxide is going to be worked out by doing 32.1 plus 16 times 3, which is 80.1. Okay, to work out the moles, so we do 32 divided by 64.1, which is 0.499 moles. The ratio, we get this from the balanced symbol equation. So the ratio is 2 moles of sulfur dioxide and it forms 2 moles of sulfur trioxide. So it's a 2:2 ratio, which means it's the same. So the number of moles of sulfur trioxide is going to be 0.499 as well. And then to calculate the mass, you're just going to multiply these two numbers together. So you're going to times that by 80.1, which gives you 39.9875, which we're going to round to 3 significant figures, which is 40.0 grams. Okay? Limiting reagents. So often in a chemical reaction, in fact usually in a chemical reaction, one reagent is in excess. This is to ensure that the other reagent, which is the limiting reagent, reacts as fully as possible. Okay? The limiting reagent will determine the mass of products able to be produced. So this is the type of question where you might get asked to calculate which one is in excess, or you might be given information on two of the reactants, or essentially you might be just directly told this is a limiting reagent, determine which it is. So, an analogy. If I have a loaf of bread which contains 20 slices, which apparently the average loaf of bread does contain 20 slices, and I bought a packet of sliced cheese which had 8 slices of cheese in, I wanted to make some cheese sandwiches. The cheese sandwich contains 2 slices of bread and 1 slice of cheese. How many cheese sandwiches could I potentially make? Well, if I've got 20 slices of bread and 8 slices of cheese, the maximum number of cheese sandwiches I can make is actually determined by the amount of cheese that I have. If I have 1 slice of cheese and 2 slices of bread, the maximum number of sandwiches I can have is 8, and I'm going to be left over with a couple of slices of bread. So in this example, the cheese is the limiting reagent, and this determines how many cheese sandwiches you can make. The bread is in excess, so it doesn't matter that you've got extra slices of bread. I mean, you could argue that those are the crust, and that's a whole different argument altogether. So let's have a look at this in terms of a chemical reaction. So cheese plus 2 slices of bread makes a cheese toastie, which is BD2CH. I've got 8 slices of cheese, 20 slices of bread, and I want to know how many cheese toasties I can make. So the chemical equation tells me 1 mole of cheese reacts with 2 moles of bread. Okay, so I have 8 moles of cheese, which would need 16 moles because 1 to 2 is multiplying by 2. So 8 slices of cheese need 16 slices of bread. Well, I've got 20 slices of bread, so I'm actually going to have some bread left over. Okay. The other way you could look at this is you could say, well, 20 slices of bread could in theory make, because it's a 2-to-1 ratio, so this time I divide by 2, so 20 moles of bread would need 10 moles of cheese, but I don't have 10 moles of cheese, I've only got 8. So therefore the cheese, there isn't enough cheese to react with all of this bread, so therefore the cheese is the limiting reagent. So let's have a look at an example that doesn't involve cheese and bread, because I don't know about you, but I'm getting a bit hungry. So this example, 250 kilograms of iron 3 oxide reacted with 30 kilograms of carbon. Calculate the maximum mass of iron produced. So in this reaction, we took 250 kilograms of iron 3 oxide and we had 30 kilograms of carbon. So the first thing we need to do is work out the relative formula mass of iron oxide and carbon. Okay, so that is going to be 55.8 times 2 plus 16 times 3, which equals 159.6, and carbon is just 12. Okay, so that's the MRs. That's the first bit. The second bit is to work out the moles. So I'm going to work out the moles of Fe2O3. So moles is equal to mass over formula mass. So the mass in the question is 250 kilograms. So it's 250,000 grams. It's important that we use 250,000 to calculate the moles, divided by the MR, which is 159.6, which gives us an answer of 1566 moles. Then we need to work out the moles of carbon. Again, that's going to be mass over formula mass. So the mass of carbon is 30 kilograms, which again I need to convert into grams, which is 30,000 grams, divided by the MR. Well, technically it's the AR, but it's 12, and that equals 2,500 moles. Okay, so The next thing we need to do is we need to work out which of these is indeed the limiting reagent. So we need to think about the ratios. So I've got 2 moles of iron oxide reacting with 3 moles of carbon. So I'm just going to write this again here. 2 moles of Fe2O3 reacting with 3 moles of carbon. So what that tells me is 2 of these need 3 of these. So how do you get from 2 to 3? Well, the way I always do this is the moles here, you're going to divide it by itself, and then you're going to times it by this number here. So to go from there to there, you're going to divide it by 2, which is 1, then you're going to times it by 3. Okay, so we worked out that the moles of Fe2O3 was 1566 moles. So therefore the moles of carbon that would need is 1556 divided by 2 times by 3, just like we did here, which equals 2349 moles. Okay, so this tells me that if I had 1566 moles of iron oxide, I would need 2349 moles of carbon. Now I actually have 2500 moles of carbon, which is more than is needed to react with this number of moles of iron oxide. So therefore we can determine that the carbon is in excess in this example. Okay, we can also do this another way just to confirm. So we can also say that the moles of carbon, which is 2500, would need how many moles of Fe2O3? So to do this, we're going the other way in the ratio, so we're going from 3 to 2. How do we get from 3 to 2? Well, we divide 3 by 3 and then we times it by 2. So that needs 2500 divided by 3 times by 2 moles of iron oxide, which is how many moles? 1667 moles. How many moles of iron oxide do I have? I have 1566 moles. So that's how many moles I would need. This is how many moles I have. I haven't got enough moles of iron oxide, so that again confirms that this is the limiting reagent and the carbon is in excess. Okay, once we know which the limiting reagent is, we can do the calculation. So I know that the limiting reagent is going to determine how many moles of product I can make. So it's the iron oxide at 1566 moles, which is going to determine how many moles of iron I can make. So what do we do next? So we need to go back to the equation. So we know 2 moles of iron oxide makes 4 moles of iron. So how do we get from a 2 to a 4? Well, we divide it by 2 and times it by 4. Okay, so we need to do that to the number of moles of iron oxide. So we do 2 moles, so we do 1566, whoops, wrong pen, divided by 2 times by 4, and that will give us the moles of iron, which is equal to 3133. And then to work out the mass is mR times moles, which is the mR of iron, which, well, technically the AR, which is 55.8. So we're going to do the mR 55.8 times the moles, which is 3133, and I'm running out of space, I'm going to go up here. So 55.8 times 3133 is 174812 grams. Okay, we're going to give our answer to 3 significant figures and in kilograms. So I divide this by 1000 and then give it to 3 sig figs, which is 175 kilograms. Okay, so I thought the next thing we could do is take a look at some exam questions. Now actually most of the questions we've already been through today are exam questions, So as always, I would recommend having a go at them yourself and then looking through how we do the worked examples. So question 1. A student heated a solid sample of Na2CO3.xH2O for 1 minute to remove water and determine a value for X. The diagram of the apparatus used, the table shows the results recorded. So we've got the mass of the empty evaporating basin, which is really important that you know, the mass of the evaporating basin and the solid before, so this is the hydrated salt mass. And then we've got the mass of evaporating basin and solid after heating for 1 minute, so this is the mass of the anhydrous salt plus the crucible. Plus the crucible in that case as well. So obviously to work that out we need to take off the mass of the crucible. Use the data in the table to calculate a value for X in the formula Na2CO3.xH2O. Give your answer to 2 decimal places and that's worth 5 marks. Okay, so first thing we need to do is we need to work out the masses involved. So we know the mass of the empty evaporating basin is 24.35 grams. So the first thing we can work out is the mass of the hydrated salt. So the hydrated salt, which is the Na2CO3.xH2O, and that's going to be the mass of the before you heat, which is 25.47 grams, minus 24.35 grams, which is the mass of the crucible, which gives you an answer of 1.12 grams. Okay, so the next one we can work out is the mass of the anhydrous salt. So this is the mass of the salt after heating. So we still need to take it away from the mass of the crucible. So it's going to be 24.92, which you can just about see here, minus the mass of the crucible, which is 24.35, and that will give us a mass of 0.57 grams. That is the mass of the Na2CO3 without water. So therefore the mass of the water, which we removed, is 1.12 grams minus 0.57 grams, which equals 0.55 grams. Okay, so remember we did this before in a table. So we took the Na2CO3 and we've got the water, and then we did mass is Mr. Moles and then the ratio. So the mass of Na2CO3 we worked out is 0.57 grams. That's the anhydrous salt minus the crucible. The mass of the water we just calculated being 0.55 grams. The MR of Na2CO3, you look up the numbers in the periodic table, and that gives you 106.2, and water is 18. Moles we calculate by dividing these two numbers. So 0.57 divided by 106.2 gives you 5.367 times 10 to the minus 3 moles. And the moles of water is 0.55 divided by 18, which is 0.0306. We identify which is the smallest. The smallest number should always be this. So you divide that by itself, 5.367 times 10 to the minus 3, which will give you 1. And then the water, which is 0.0306, divided by 5.367 times 10 to the minus 3. Now I leave these numbers in the calculator, store them in the memory, and divide them by the full numbers, which will give you an answer of 5.69 to 2 decimal places. Now obviously if you rounded your answers, so if you did 0.0306 divided by 5.367, you would get a slightly different answer. So on the mark scheme there is a range given, but 5.69 is what you get if you use the full numbers in your calculator. Remember, the question did say to 2 decimal places. Although you might be very used to giving this as an integer, do what the exam asks you to do. The 5th mark is for an answer to 2 decimal places. So that's 5.69. Part B. The correct value for x is 10. So we got 5.69. Suggest a reason for the difference between the experimental value for x and the correct value, 1 mark. Let's have a look at the apparatus again. So the student heated a solid sample of zinc for 1 minute to remove water and determine a value for x. How do we know they removed all the water? Where did they reweigh it? Where did they heat to constant mass? They didn't. So, suggest a reason for the difference in mass. There was probably still some water left in it. They didn't heat till constant mass. So there's some water left in it. Not all the water was removed. Okay, remember I said it's really important you heat till constant mass. So suggest how the procedure could be improved using the same apparatus to give a more accurate value for x. Well, if they didn't heat to constant mass in part B, then it's safe to say that the best way would be to heat until constant mass. Or you could say heat, reweigh until the mass is the same. But this little phrase here, heat to constant mass, is a belter. Okay, so hydrated strontium chloride SrCl2.6H2O has a molar mass, which is MR, of 266.6 grams per mole. The student heated 5.332 grams of SrCl2.6H2O. That's the hydrated salt. The SrCl2.6H2O loses some of its water, so it's not being heated to constant mass, and it forms 3.892 grams of solid product, which is not quite an anhydrous salt. Use the information to determine the formula of the solid product. So this is different because we can no longer assume that this is the mass of SrCl2. This is the mass of SrCl2 with some water still there. Okay, but we don't know what that is. But we do, this is where it's different, because we do know the MR of this one. So the MR of this is 266.6. So the first place I would start is to work out the moles of SrCl2.6H2O, which is 5.332 divided by 266.6, which equals 0.02 moles. Right. Then, what next could we do? Well, we don't know the MR of the SrCl2.xH2O in this product here, so we can't work out the moles of this because we don't have the mass. We don't know the MR of this. This is ultimately what we're trying to find out. We can deduce that the mass that's been lost between here and here is due to water. So the next thing I would do is to work out the mass of water that has been lost. So the mass of water lost is 5.332 grams minus 3.892 grams, which equals 1.44 grams. Now we do also know the MR of water is 18, so we can work out the moles of water. So the moles of water lost is 1.44 divided by 18, which is 0.08 moles. So if I know how many moles of SrCl2.6H2O I had at the beginning, and I know how many moles of water I had produced, then it's safe to say that I can work out whatever this is here, okay? Because this is X, and this is going to be 6 minus X moles of water in this formula. So 1 mole of this makes X moles of this. So I had 0.02 moles of this, and it made 0.08 moles of this. So let's get this into a number that we can deal with. Divide by the smallest, as usual, which gives us a ratio of 1 to 4. If I know that I had 4 moles of water, then it follows that I must have had 6 minus 4 moles left, which gives us the formula SrCl2.2H2O. And that is the formula of what's left. Okay, so that brings us to the end of this video, amount of substance 3, empirical formulas, reacting mass and limiting reagents. So we've looked at how you can calculate empirical formula. We've looked at calculating X in hydrated salt. I feel like this is what we spent most of our time doing. And then we looked at calculating masses from balanced equation and identifying the limiting reagent. So my thoughts is I'm going to do one more video where we're going to look at concentration calculations, and then I'm going to do a 5th one where we bring all of this together and we look at some exam questions that stretch across the whole of the moles topic. Okay, thank you again. I really hope these are helpful, and again, as always, leave any comments or any suggestions for further videos or improvements below. Thank you again. Bye bye.